Hi everyone! So today we're just going to do some examples. Okay, so here are 5 examples I'd like you to consider. So go through them. Are they bijective? Why or why not? If they're bijective, what's their inverse? So I'm hoping that me going through this will be helpful to you today. I heard that some people are having problems with functions whose domain/codomain are Cartesian products and like the piecewise functions that look like this, where it depends what element you're plugging into it, what you get out. Um, so yeah, so I'm gonna go over some of these, and I hope that it helps. So with our first example, F going from R cross R to R. So remember, this R cross R means, let's go over what the definition of that is. So this is a set, and it's of ordered pairs, say x, y, and so ordered pairs just means that it really does depend what order they're in. Okay, such that x, well, let's do in general. Let's do like some A and B, they're sets. Okay, x is in A, B, y is in B. Okay, so this particular Cartesian product is the real plane. So you can imagine this is the x-axis, this is y-axis. So inherently you should know that order does matter. For example, 0, 1 is different from 1, 0. Okay, those 2 points are different. So that's why it's called ordered pair, this thing here, because the order does matter. Okay, but for this function, actually that's going to be to its detriment. Okay, so this is not going to be a bijective function because it's not injective. Okay, so it is surjective because you have some y. Sorry, my rabbit is a little sick, a little under the weather. She's sneezing. So so you have some y and r. You could consider like 1 comma y. So f of 1 comma y would equal y. So I'm not doing a proof right now. I'm just kind of sketching what my thought process is and how you could go about proving it. So that would show that it's surjective. But how about injective? Well, let's say 2 comma 0 is not equal to 0 comma 2, or you could even say 0 0. Like 0 is a big one, but then also you could think about like 1 comma y and y comma 1. Those both go the same thing. But f of does equal f of 0 comma 2. So in general, f of a comma b does equal f of b comma a, whether or not those two ordered pairs are equal. So it could be if a equaled b, which is possible when, when we have r cross r. Okay, so not injective, so then it can't be bijective, so now we can't even think about its inverse function. Okay, so here we have the g from the natural cross naturals to naturals cross naturals. G of x comma y is equal to y comma x. Okay. So let's see, surjective. And so remember, these are just sketches. It's not even close to a proof. So let's say you picked someone out of here. You'd say a comma b in there. Okay. Then this is just loose notation. I'm saying like it's an element of this thing up here. Then you would just flip-flop them, right? You would say G, consider that, and that's going to equal A comma B. Beautiful. Surjective. How about injective? Okay, well, assume, say G of alpha comma beta equals G of A comma B. Let's do that. Then beta comma alpha equals B comma A. Okay, so for these to equal, let's use some nice colors. Then these two things have to equal, and these two things have to equal. Okay, so beta equals B and alpha equals A. Oops. So AB equals alpha beta. All right, so it's also injective. Woohoo, so that means it's bijective. Great. So now that it is bijective, we can find an inverse function. Okay, so sorry, let me label it 2. All right, who would our G inverse? So our G inverse, first we need to think about where it's going, what its codomain and domain are. Okay, so let's think about, okay, well, if I want to, so here's what I'm trying to think about ahead of time. I want G inverse of A comma B to equal A comma B, and I want this to also happen that way. And you can use different variables that I'm using. It doesn't really matter that much. Okay, but what does G do? So I'm going to focus on this one for right now because I know what G does. So this is, sorry, I should still label it even though it's just a sketch. This is what I want. Okay, so I'm sketching right now. So I want this to happen. I know what G does. So this thing equals G inverse of B comma A, and then I want it to end up looking like A comma B. Oh, okay, so why don't I just have G inverse flip-flop again? Gorgeous. So G of B comma A equals A comma B. Okay, so now that I erase this middle equals, I can get rid of this want, and this is actually my proof now. Okay, cool. So this works as our inverse function. Okay, how about this little friend that we have here? Our function from the integers to integers, where it takes positive and 0, non-negative, integers to 2t and negative integers to 2t minus 1. Okay. So let's see. First we want to think about if it's bijective. So injective, positive to positive stuff on as a one. So this is an injective function, taking positive reals and 0 to 2 times that. And then this thing is also injective, taking a negative thing and sending it to 2 times itself minus 1. That's also injective. Okay, so it is injective because each of its that's what it's called, piecewise functions. So each of its pieces are injective. So it is injective, but it is not surjective. So let's say, so if you notice, it's taking all positive things to evens, and it's taking all negative things to odds. Okay, so because that's just by the definition, because t's are all going to be integers. So we could consider 3. Maybe I would say something like when h of t is bigger than or equal to 0, let's just say bigger than 0, then t is bigger than 0. But when t bigger than 0, bigger than or equal to, but that's fine, then h of t is even. So there exists no t such that h of t equals 3. So notice how I'm setting this up. I'm not just saying whenever t is positive, then all this happens. I'm saying when h of t is positive. Because what if when t is negative, t being negative still lets h of t be positive? Okay, so you really want to round everybody up. And still, this is just a sketch. I don't claim that this is like the best proof I've ever written. Okay, so not surjective, therefore can't be bijective. So don't even think about the injective. I mean the inverse. So I know it's terrifying seeing division when we're talking about integers. I know it makes me so nervous every time I see it. But that's okay because we're only talking about even integers. So you can always divide an even integer by 2 and still get an integer. Okay, say k of s equals k of t or something, I'm not sure. So then s divided by 2 equals k divided by 2. Well, integers are closed under multiplication, so that means you can multiply an integer by an integer and you still get an integer. Well, luckily for us, this is an integer, so we can multiply both sides by 2, so then we can get s equals k. Boom, roasted. Okay, surjective. Pick some integer, let's say z, because I'm very creative. Maybe you would want to do some scratch work for this, but basically what I'm going to do is I'm just going to consider 2z, which is in the integers. So k of 2z, well, it's in the even integers, in fact, even integers. So that's what's really important. You always want to specify when you're trying to show something is surjective. You always want to say why that thing that you're about to plug in your function, why you're allowed to, why that's in the domain. Okay, so it is an even integer by definition because this is an integer and you're multiplying by 2, so it has to be an even integer. So that's going to be 2z over 2, and you guessed it. We're just going to do that. Boom, roasted. So it's bijective. Okay, so now is where the fun begins. How in the heck do we do the inverse? Well, you probably already guessed it. We're just going to multiply by 2. If you didn't guess it, that's okay. C'est la vie. All right. So we got to show this thing here. So we have k of 2x, and that's just going to be x. K inverse of k of x. And so what's kind of nice about proving something's bijective is that you kind of already have thought about what the inverse function is going to be. So my advice is if you're ever on an exam and you're really having a hard time coming up with the inverse function, try maybe just doing like a brief sketch of why it is surjective, because the surjective is usually when you find the magical key of what's the inverse. Okay, I changed this last one. Let's see, let's say m of L equals m of k or something, I don't know. So then, so those are going to be integers, okay? Either m of L even or odd. If ml even. All right, so if ml is even, then L must be odd, since that's the only way to get an even output. Since even minus 1 equals odd. So, and 2 times any integer is always going to be even by definition. Okay, so k also odd. Therefore, ml equals L 2L equals 2k equals mk. Okay. So then L equals k. Boom. Yay. Cool, cool, cool. All right. So how about if ml odd, then L even. So L and k even. So remember, this is just a sketch. I would write it probably a little bit nicer. But okay, so L and k are even, so then we have ml equals mk, meaning that L minus 1 equals k minus 1. Well, we could just add 1 to both sides. We get that. Boom, roasted. So it's injective. Surjective. So surjective It is not. Not surjective. Whoops. Okay, so it's not surjective. And I even fooled myself into thinking that it was for a second. But think about it. How about 8 in the integers? Who are you going to... So what odd number are you going to multiply by 2 to get 8? Or what even number are you going to minus 1 from to get 8? So your only two options would be 9 and 4. But 4 is even and 9 is odd. So that wouldn't work out. Okay? And you just want to explain that. So then we don't have an inverse.